I'm sorry that I gave you all a heart attack. That's not supposed to happen. I'm sorry. We are in chapter two, describing motion. And the last time we were working in chapter two, I had gotten through talking about how we're going to define instantaneous velocity, how we're going to define instantaneous acceleration. So I want to recap with the notes that I have here. I want to recap exactly what we found and reiterate something to you. So luckily, like I said, I already did this lecture twice today, so it's not a problem. First off, we had the average speed. The average speed we marked as S with a bar over it, and we defined that to be distance traveled divided by time taken. So I mean time taken to travel that distance. Now that literally means the distance. Like if you're driving in a car, the odometer moves forward while you're moving in forward, and then if you stop, put the car in reverse, and start rotating, start rolling backwards, the odometer in principle should roll forward some more still. In principle, it should be able to do that. And if I remember correctly from Ferris Bueller's Day Off, it does not roll backwards by you putting in reverse. Hopefully, it doesn't work that way. But that's the key thing to remember is the total distance you traveled, whether you were going back and forth 1,000 times or not. You have to count every bit of that motion. Additionally, we have an average velocity, which is going to be a lot more complex and more weighty once we get to chapter three, where we talk about the vector quality of the quantity. So average velocity is really an average of a vector quantity, but in one dimension, the vectorness of it, which means it has magnitude, meaning a size, and a direction. In this case, since it's one dimensional, it's just going to be a positive sign if it's going the direction you chose, the positive x direction, and it's going to have a negative sign if you chose, if it's traveling in what you chose as the negative x direction. And that is going to be written as v with a bar over it, and it's actually the displacement divided by the time taken. And that translates to delta x over delta t. And I warned you guys that delta always means change in, and therefore, unless I explicitly tell you otherwise, it means final minus initial. Okay. So that's a big difference, and you're going to see a difference on that in a second. The instantaneous velocity, v instantaneous. So the word is instantaneous. Okay, that's what I'm saying here. We also call that v as a function of time, and that turns out to be the limit as delta t approaches zero of delta x over delta t. And you guys have had Calc 1, so you know that's also equivalent to dx over dt. So that's the instantaneous velocity. Uh, that was pretty much all we covered, and we did some examples with it. But now I need to go on from there. I'm going to cover the average acceleration, which I bet you can guess the formula for. Average acceleration is equal to a bar. And just like it was delta x over delta t was the average velocity, the acceleration is supposed to be the instantaneous, or excuse me, it's the time rate of change of velocity. So in this case, we'd call it delta v over delta t. Okay. And again, that delta means final minus initial. So you could write that as v final minus v initial over T final minus T initial, but normally everybody just calls that thing in the bottom T or delta T. Either one's acceptable. But another way I could write it without any ambiguity is I could just write V minus V0 over delta T. That would be accepted as well. But that's what the average acceleration is. And you might guess, based on what you've seen so far, that the instantaneous acceleration is equal to what we would call A of t. And in this case, if we take the limit as delta t approaches zero of delta v over delta t, we end up getting dv dt, which also happens to be d2x over dt squared. So those are our equations that we can start from right now. I'll go ahead and box them off, and those are what we call our kinematic equations and definitions so far. So these are definitions and quote unquote kinematic equations. And now I'm going to show you some examples, and I'm going to start off with example 2.4. So example 2, I usually write it as 2.4. Your book is calling it 2-4. But given x as a function of t, it says a jet engine. This is where I'm reading the example from the book. If you have the book open electronically, that might help you. It says a jet engine moves along an experimental track, which we call the x-axis, as shown in figure 213a. We will treat the engine as if it were a particle. Its position as a function of time is given by x is equal to at squared plus b. So x of t is equal to at squared plus b, where a is going to be equal to 2.10 meters per second, which is meters per second squared, and b is going to be 2.80 just plain meters. You can see that's what it has to be because the left-hand side has to be x, which is measured in meters or is in dimensions of length, and at squared has to have the a multiplied by t squared, which t is going to be in seconds, and has to spit out meters. And the only way a t squared could spit out meters is if a is meters per second squared and t is in seconds. Similarly, b has to be meters, so that's why it's 2.80 meters. It says part A, determine the displacement of the engine during the time interval from T1 equals 3.00 seconds to T2 equals 5.00 seconds. So part A is delta X equals question mark for T1 equals 3.00 seconds and T2 equals 5.00 seconds. Part B, they want us to calculate the average velocity during that time interval. So we're going to say V bar is equal to question mark. And then part C, they want to determine the magnitude of the instantaneous velocity at t equals 5 seconds. So they want specifically V instantaneous, which I'm going to write V of 5.00 seconds. That's what they're wanting there. Now, there is a little danger here when you're calculating something like this and they give you x as a function of t. You have to at least a little bit imagine what the graph of the x of t is going to look like. I'll show you an example where it gets more complicated. This example actually works out very simply, so I'm just going to go with it. But I'm also going to show you another example that's makes it a little more confusing, but it's got to be addressed or you actually get it wrong. So our solution is the following. We're going to make use of all these things that we already did, those equations up there. I'm not going to take the time to write them because I just finished doing that. But for part A, what I'm going to do is I'm going to just mention that the position as a function of time for this is actually looks just like this. It hits at 2.80 meters, and then it's just a parabola going up. So what I want you to know is because the time interval that we're looking at, because this is 0 seconds and this is, let's say, 5 seconds, and this might be 1, 2, 3, 4, 5. The interval that we're looking at seems to be between 3 and 5. There's no maxima in there. If there was a maxima in there, then it would be a little bit more complicated discerning the difference between distance traveled and the displacement. The displacement, remember, is supposed to be you imagine where you started as if it were some home position, and then you imagine where you ended is your final position. And when you want to calculate the displacement, you have to find the distance like a bird would fly from home to your final distance. Not how far you traveled, but how far your new position is from your old position. So in this case, delta x is going to be x of 5.00 seconds minus x of 3.00 seconds. If you plug in x of 5, what you're going to see, or if you plug in 5 into x of t, you're going to see that becomes 2.10 meters per second times 5.00 seconds squared. You can see that when you multiply that, that's just going to give you meters. And then you're going to also add 2.80 meters. If you square 5, that becomes 25. 25 times 2 is 50. And then 50 times point 0.1 is 1/10 times 1/5. That'd be 1/10 times 5 would be 1/2. So this is like 20.5, 20 points. Let's double check. There's a good chance I make a mistake here. So 2.1 times 5 squared, just to be careful so I don't make a mistake. That's 52.5. And x of 3 is going to be 2.10. I'll leave off the units this time, times 3 squared plus 2.80. 2.1 times 3 times 3 plus 2.8. Oops, I forgot to add the 2.8 last time. That's why that number didn't look familiar. This one turns out to be 21.7. So let me check this. I did make a careless mistake. I just multiplied instead of multiplied and then adding. So I'm going to take 5 times 5 times 2.1, and then I'm going to say plus 2.8, and that gives me 55.3. That's why I was remembering a different number because I forgot to add. 55.3 meters. So delta x, which is what part A was supposed to be, should be 55.3 meters minus 21.7 meters. And that gives me 33.6. Ooh, 33.6 meters. So that's part A's answer. Part B's answer is we want the average velocity. So part B, V bar is equal to delta x over delta t. That's going to be 33.6 meters divided by 2.00 seconds because 5 seconds minus 3 seconds is 2.00 seconds. So if I divide this 33.6 by 2, we end up getting 16.8 meters per second is V bar. So that's our average velocity. Now, the instantaneous velocity at 5 seconds is just the derivative of the velocity as a function of time. So we can see that the velocity as a function of time, if I write it up here, v of t is equal to dx over dt, which is d by dt of at squared plus b, which ends up becoming just 2at. So for part C, v of 5 is equal to the instantaneous velocity. So it's going to be 2 times 2.10 times 5, and that gives me 21.0 meters per second is the instantaneous velocity at 5 seconds. Notice the instantaneous velocity does actually still change. It's still a function of time. So at t equals zero, it actually has a velocity of zero, whereas t equals one, it's a little bigger. T equals two, it's a little bigger, so on and so forth. Anybody have any questions on that? All right. So just to go back to what I was talking about, had you done the same problem and your x is a function of t, I'm going to call this counter example. If we had had a x as a function of t that looked something like this, and let's say this was 5 seconds, and let's say this was 3 seconds, let's call this one, let's call this two, let's call this three, and let's call this zero point 0.9. Okay. Now, in this case, the total distance traveled is, you can see from 3 seconds, it went to about from 2 to about 2.8. And you can see that after that, it went from 2.8 to 5, down to zero point 0.9. Okay, at 5 seconds. So the distance traveled is actually, they went from 2.0 to 2.8, so that's about zero point 0.8 up. And then they went from 2.8 to zero point 0.9, so that's about 1 point, excuse me, that's about 2.9 up. So, or down, I should say. So the total distance traveled in this case would be zero point 0.8 plus 1.9, which would be 2.7. So that would be the distance traveled, which is what you'd use for the average speed. But the delta x in this case is just going to be where you started, which was at x equals 2 meters, and where you ended was at x equals zero point 0.9 meters. So delta x in this case would be just 0 0.9 meters minus uh, 2.0 meters, which is negative 1.1 meters. That would be your displacement there. But notice how if you tried to calculate the speed, you wouldn't know that that distance is bigger than 1.1. So that's what I mean by you have to actually plot the x as a function of t before you calculate the average speed or the average velocity, because displacement is very different from distance traveled. Now, hopefully that's enough for you guys to understand. But what's really going to happen is later on you're going to run into a problem in your homework that you are getting mixed up, and hopefully you'll remember this then, and it'll come in handy. It's not going to make any better sense to you until you actually run into an example where you have to do it. So keep that in mind. Now that we have all this, these equations that I've given you, I'm going to work another problem. In this case, it's example 2.5. So let's say example 2.5. This example says average acceleration. A car accelerates along a straight road from 90 kilometers per hour in 5 seconds. So actually, I think I missed a key word there, and it's important. A car accelerates along a straight road from rest to 90 kilometers per hour in 5.0 seconds. What is the magnitude of the average acceleration? So this is a simple average acceleration problem. What we know is that v initial, notice I had to infer this. They implied it, and I had to infer that it started from rest, which meant I had to infer that the initial velocity v0 is in fact 0 meters per second. The final velocity, which I'm just going to call as v because that's less subscripts, is 90 kilometers per hour, which I'm going to assume is to 2 sig figs. So I just put that dot there to remind us that it is 2 sig figs. So now I have that, but to be honest with you, that doesn't help me very much. I need it to be in meters per second because I'm going to deal with time in seconds as well. This V is 9 90 kilometers per hour, and that happens at a time t equals 5.0 seconds. So again, that's 2 sig figs. And the solution for this involves us using A is equal to V minus V0 over delta t. So we now have delta t, which is clearly the same thing as t, but I also have to deal with this 90 kilometers over 1 hour. And the way we deal with it is we take 1 kilometer and put it in the bottom, and that's equal to 1,000 meters in the top. You can see that by multiplying like this, the kilometers cancel out with the kilometers. But now I also got to get rid of the hour. In fact, the hour is the more important thing I had to get rid of. And what I know is that 1 hour is equal to 3,600 seconds. So you see, you're going to multiply by 1,000 and divide by 3,600. So really, all you're doing in going from kilometers per hour to meters per second is dividing by 3.6. So I'm going to say this final velocity v0 is equal to, the math works out to be 25.0 meters per second. That's what 90 kilometers per hour is. Okay. So now I can calculate the average acceleration. A bar is equal to 25.0 meters per second. That's not a sig figs, hence I underlined it. Over 0.0, or minus 0.0 meters per second. All that divided by 5.00 seconds. Again, that second zero is not a sig fig. 25 divided by 5 is 5.0 meters per second, and that's my average acceleration. Anybody have any questions on that one? By the way, the unit is actually 5 meters per second. I didn't write the part. 5 meters per second per second. You could also write that as meters per second squared. That's the easiest way to write it. But again, I want you guys to think of acceleration as meters per second, because for instance, at an acceleration of 5 meters per second, that means if it really was a constant acceleration, which, cars generally don't have constant acceleration for very long periods of time anyways, not for more than a couple seconds. But if it was a constant acceleration, then what that means is at t equals 0 seconds, it would have a velocity of 0. After 1 second, it'd be going 5 meters per second. After 2 seconds, it'd be going 10. After 3 seconds, 15. After 4 seconds, 20. After 5 seconds, 25.0 meters per second. So you see that the velocity changes by 5 meters per second each second it's traveling. So that's why I want you guys to read it as meters per second per second. They go to a They go to a nice conceptual example next. That's conceptual example 2.6. And it says, if the velocity of an object is 0, does it mean the acceleration is 0? So I want you to understand that, for instance, when I throw an object up, again, we don't talk about the time while my hand's touching it, but the instant it leaves my hand, it starts slowing down, slowing down, slowing down, slowing down, and it comes to a stop. At that point, the velocity is 0. Then if you wait a split second later, it's going to start falling back down, back down, back down. And in fact, the way it's going to do it is it's going to change its velocity by 9.80 meters per second each second that it's traveling, because that happens to be the acceleration due to gravity. On the way down, that acceleration is causing the speed to go from 0 to a higher number. On the way up, it's causing that velocity to go from a high number to a smaller number. Okay. Now, in this case, when it's at the top, the velocity is 0, but it turns out that when you throw an object, once it leaves your hand, if you're ignoring air resistance, the acceleration is 9.8 pointing downward the whole journey, So the fact that the velocity is 0 for a split second does not mean the acceleration is 0. But if the velocity is 0, and then you wait, a tenth of a second and it's still 0, and you wait another tenth of a second, it's still 0, then yes, the acceleration is 0. So flipping through 0 velocity does not mean the acceleration is 0, but if it's a fixed velocity of 0, then yes, the acceleration is also 0. Then in part B, it says, if the acceleration is 0, does it mean the velocity is 0? And that's also not true. If the acceleration is zero, that just means it's not speeding up, slowing down, or changing directions. That's the three ways that something can accelerate. It can speed up, it can slow down, or it can change its direction because acceleration is a change in velocity, and velocity is a vector quantity, therefore it has a magnitude and a direction. So acceleration can be zero as long as, or excuse me, the acceleration is zero, and that means the velocity could be a constant. It could be a constant that's zero, but it could be a constant that's 50 miles per hour as well. Okay. In fact, there's a course called statics that you mostly learn about things that aren't moving, but specifically you're solving problems for things that aren't accelerating. In fact, if you had to build a house that was going to be on the back of a flatbed truck and you designed it according to the statics that you learn in a statics class, it will work equally as well on the back of a truck traveling at 50 miles per hour. You just have to then make sure it can withstand 50 mile per hour winds. Or if it's going to go 120, you got to make sure it can withstand 120 mile per hour winds. Any questions on that?
When with this one, when it comes to like problems that we may see, are we like, is there a certain way that those are going to look like to be able to indicate that the velocity is a constant of zero? Like, will it
Yes,
just
they'll
describe?
say an object has a constant velocity, and then that lets you know, oh, the acceleration must be zero.
Okay, okay,
Yeah, they'll say words like that. And if it's any question, if you're sort of doubting it, that's one of the questions that I normally allow students to ask me too. So always ask if you don't understand something,
okay,
and if it's something I can't answer, I'll make sure I let you know I can't answer it.
okay. Thank you.
Okay, you're welcome. All right, moving on to example 2.7, and this is a little misleading, so I'm going to show you it and a counter example, but it says car slowing down. An automobile is moving to the right along a straight highway, which we choose to be the positive x-axis. Then the driver puts on brakes. If the initial velocity when the driver hits the brakes is v1 is equal to 15 meters per second, and it takes 5 seconds to slow down to v2 equals 5 meters per second, what was the car's acceleration? So what we have is V1 is equal to 15.0 meters per second at uh, t equals 0 seconds, and V2 is equal to 5.0 meters per second at 5.0 seconds. What they want to know is what is the car's average acceleration? A bar is equal to question mark. So this is one of those cases where you're going to get a negative acceleration, and this car happens to be slowing down, but I don't want you to make the conclusion that a negative acceleration means it's slowing down. I'm going to show you a counterexample in a second where a negative acceleration actually means it's speeding up. So in this case, it's A bar is equal to V minus V zero over delta T. Just using these as we want, as we have seen, I'm going to take the final velocity, which is 5.0 meters per second, and I'm going to subtract from it the initial velocity, which is 15.0 meters per second, and I'm going to divide that by the time change, which is 5.0 seconds. 5 minus 15 is negative 10, so I'm going to get negative 10.0 meters per second per 5.0 seconds. That's going to be negative 2.0 meters per second every second, and that's our A bar. So that's our average acceleration. You can see it is negative, and you can see it is slowing down. A counter example, what we're going to do is imagine that the car instead was going in the negative direction. So evidently going to the right on the straight highway is what we chose to be the positive X direction. Now what we're going to say is the car is going to actually go in the negative X direction, and it's going to actually start at 5 meters per second in the negative direction and end up reaching 15 meters per second in the at the end of 5 seconds. So here's how we're going to do that. We'll say V initial is negative 5.0 meters per second. Notice the negative is the fact that we're doing one-dimensional motion and velocity is a vector quantity. So the negative indicates that its direction is in the negative direction. The magnitude is still the positive quantity. We don't have negative magnitudes, not in classical physics. The final velocity is going to equal negative 15.0 meters per second, and delta t is still going to be 5.0 seconds. So that a bar is equal to negative 15.0 meters per second minus negative 5.0 meters per second divided by 5.0 seconds. Negative 15 plus 5 is going to be negative 10.0 meters per second divided by 5.0 seconds, and therefore you get negative 2.0 meters per second is equal to a bar. So now you've seen an example where a negative acceleration is actually something speeding up. Anybody have any questions on that? Okay, I've already given you the equation for the instantaneous acceleration, so I'm going to jump into example 2.8. Example 2.8 says acceleration given x of t. We're using the exact same equation we did on that previous example, so this is 2.10 meters per second times t squared plus 2.80 meters. That's our x of t. What we want is it says a particle is moving in a straight line, so the position is given by the relation that I just wrote down. A, it's calculate its average acceleration during the time interval 3 seconds to 5 seconds. So A bar from T1 equals 3.00 seconds to T2 equals 5.00 seconds. And then part B, they say calculate its instantaneous acceleration as a function of time. So in this case, we want A of t equals question mark. What we're going to use here is A bar is equal to V minus V0 over delta t, and we're going to use A of t equals A instantaneous, which equals dV dt, which equals d2x over dt squared. So starting off with A, I have to actually calculate the V at a specific time. So I need a V of 5.00 seconds, and I need V of 3.00 seconds before I can calculate any of that. V of t is equal to dx dt, which equals d by dt of 2.10. Notice I'm dropping the units right now for ease. Yeah, take the derivative of that with respect to time. I get 4.20. It still has the same units, meters per second, times t. And then, of course, the 2.80 just completely disappears because that's a constant term. So now I can say v of 5.00 seconds is equal to 4.20 meters per second times 5.00 seconds. Notice it's not squared anymore. 5 times 4 gives me 20. 5 times 0.2 gives me 1. So this is going to be 21.0 meters per second. V of 3 seconds. I know I'm talking really fast, y'all. I'm sorry if I'm losing you. Anybody have any questions since I'm going so fast?
The which part was it? The equation that you have for V of t.
Mm-hmm.
The 2.80, the plus 2.80, was that part of the example, or is that part
Yeah,
of?
yeah, that was part of this example we did earlier,
Okay.
and it's they're using it again.
Okay.
Gotcha.
Okay.
All right,
I'm
so
like, oh, it's popping up a lot.
no problem. Now we're doing the same thing, only this time it's for the 3 second mark. I'm going to leave the units off this time. And at the 3 second mark, we have 3 times 4.20. 3 times 4 is 12. 3 times zero point 0.2 is zero point 0.6. So this is going to be 12.6 meters per second. So now I can calculate the average velocity is 21.0 meters per second minus 12.6 meters per second. So that's 8.4 in the top divided by the time elapsed, which is 2.00 seconds. Remember, that's just 5 minus 3. So this should be 8.4 seconds, or excuse me, 8.4 meters per second divided by 2.00 seconds. That gives me 4.2 meters per second is the average acceleration for that time interval. Anybody have any questions on that one? Okay, so now let's calculate the acceleration as a function of time. To that end, we're going to use A of t is dv dt, which is d by dt. We just finished calculating what the velocity as a function of time was. It turned out to be 4.20 t, like that. So when we take the derivative of that with respect to time, we just get 4.20 meters per second every second is equal to a of t, which means the acceleration really is a constant. Okay. Any questions on that one? All right. So now what I want to do is I want to make use of those things that we just did. Specifically, I use the average speed. I gave you the formula for the average velocity. I gave you the formula for the instantaneous velocity and explained it. The same sort of rigmarole went with the average acceleration. And then I explained how the instantaneous acceleration was sort of an extension to the instantaneous velocity by taking the limit as delta t approaches zero. So we know these equations, but what I want to do is derive the other kinematic equations that we'll be using. And then I'm going to also derive a kinematic equation for an acceleration that's not a constant. I might do that next time, I'm not sure, but let's start off with this. So let's say, assume A is a constant. A is the acceleration. And that A is the acceleration of an object. Okay? So what that means is A is equal to dv dt. That's an equation. The left-hand side happens to be a constant. The right-hand side happens to be a derivative. It's actually what we call a differential equation. I can do anything to an equation that I want as long as I do it to both sides. The only thing you're not allowed to do is technically you're not supposed to multiply through by zero or divide by zero on either side. Okay. Both of those, even if you do it by accident, can actually make false statements. So just keep that in mind when you're multiplying by variables. If that variable becomes a zero at some point, that means that what you did by multiplying through by that equation might not have been valid anymore. So what I'm going to do is I'm going to multiply both sides by dt, like that. Okay. Now I'm going to integrate both sides. Now I could, since a is a constant, I could pull that integral out, that a out in front of the integral, and I did that earlier when I was showing my other class. But that's just because a is a constant. I'm just telling you guys, a is a constant, so just remember that. Now I could also integrate from a specific time to some subsequent time, and from a specific velocity to some later velocity. But what I'm going to do is an indefinite integral. Now, I'm taking two indefinite integrals, so I get two constants. But when I'm all done with that, I can put all the constants on one side and just have one new constant. So that's what I'm going to do. I'm just going to act like there's one constant and realize that takes care of everything. The integral of a dt is just a times t. So I'm going to get a times t for the left-hand side. The integral of dv dt with respect to dt, this is just the fundamental theorem of calculus, which says that the integral of a derivative is the original function, or the derivative of an integral is the original function. Okay, integrals undo derivatives, and derivatives undo integrals. So the integral of dv dt with respect to dt is just the velocity as a function of time. So I'm going to write v of t plus that arbitrary constant. So remember, there was a constant from the left-hand side, there was a constant from the right-hand side. I've made them into one big constant. And now what I'm going to do is, if we assume that the velocity of the object at t equals zero point 0.0 seconds is v0, then we can find that a times 0 is equal to v of 0 plus c, but v of 0 is equal to v0, so we see 0 is equal to v0 plus c, which means c must equal negative v0. So now I can rewrite this, and I'm not going to call it v of t this time. I'm just going to call it v. The fact that it doesn't have a subscript means it's the final. So now I've gotten from that v is equal to v0 plus at. And that's a new kinematic equation, but you also notice that it's not really a new kinematic equation. It happens to be the same equation you'd get if you solved the average acceleration for v. So it is a repeat of the equation we already had, but that's what we're going with now. Now we're also going to make the assumption, like we did here, that at t equals 0, the v was v0. I'm going to also make the assumption that at t equals 0, the x is x0. So also assume that at t equals 0 0.0 seconds, x of t is x0. So with that in mind, I'm going to take v of t, which is this v that we just found, which is equal to v0 plus at. I'm going to set that equal to the definition of the instantaneous velocity. Specifically, I'm going to say v0 plus at is equal to dx over dt. Now I'm going to multiply both sides by dt, and then I'm going to integrate both sides. And again, I'm going to do an indefinite integral and combine it and make it only one constant. Okay. So the left-hand side becomes v0t plus 1 half at squared. The right-hand side just becomes the x of t plus a constant. But we remember from the initial condition at t equals 0, that means we get 0 plus 0 is equal to x0 plus c. So that means x0 is equal to negative c. And therefore, we can now say x is equal to 1 half a t squared plus v0t. And remember, the negative c was on the side with x. So when it comes over to here, it'll be the positive c. So it's positive x0. This is the next kinematic equation. Okay. So these are important kinematic equations. There's actually another one. Let's call this equation 1. Let's call this equation 2. I'm going to solve 1 for t and plug that t into equation 2. Okay? So I'm going to do that. Equation 1 tells me that t should be v minus v0 over a. And now I'm going to plug that into equation 2. I've run out of room, so I'm going to do it on the next page. So x is equal to 1 half at squared plus v0t plus x0 is going to become a over 2 times v minus v0 over a quantity squared plus v0 times v minus v0 over a plus x0. What I'm going to do is I'm going to subtract an x0 from both sides, and then that gives me x minus x0 is equal to. Now, what you'll also see is the a right here and the a squared down here is going to leave an a in the bottom with a 2. So I'm going to make a common denominator because this fraction over here only has an a in it. I'm going to multiply by 2 over 2 so that it'll have a common denominator. So what I get now is the v minus v0 squared is now going to be over top of 2a, and I'm going to get v squared minus 2v v0 plus v0 squared, and that's all over 2a. Now I have plus, and remember I'm multiplying by 2 over 2, so I'm now going to have 2v v0 minus 2v0 squared, all of that divided by 2a. Everybody follow the algebra that I've done so far? Okay, so that's just squaring a binomial. That's something you should know. If you don't, you want to get there quickly. I can go ahead and multiply by 2a on both sides as well, so I'm going to do that. And for that case, I'm now going to have 2a times x minus x0 is equal to v squared minus 2v v0 plus v0 squared plus 2v v0 minus 2v0 squared. You can see that the positive 2v0 cancels out with the negative 2v0, and you also see that the v0 squared minus 2v0 squared is going to leave just a v0 squared negative. Okay, so this result is now v squared minus v0 squared. And the way I normally write this equation is v squared is equal to v0 squared plus 2a times x minus x0, like that. So that's our new kinematic equation. Might refer to it as equation three. There are some courses, algebra based or calculus based, where instructors don't allow you to use this equation at all. Okay, that's a typical thing that sometimes they'll do. The reason why is this equation can't be a vector equation. The square of a vector gives you basically a scalar, and you'd have to interpret that as a dot product, which is also called a scalar product. So it's not that useful from a vector standpoint. And in fact, when you use it, if you're solving, for instance, for the final velocity or for the initial velocity, you're going to have to take a square root. And when you take a square root, you always got to choose, is it the positive square root or the negative square root? That allows for you to make an actual error. So that's one of the reasons that people normally don't do it. Another equation that comes in handy, but it's also only true when the acceleration is equal to a constant. So is this. That is V bar. Actually, I should write it in blue so I can keep it consistent. There I go, trying to write in blue. All right. The average velocity is equal to the initial velocity plus the final velocity divided by 2. Again, these equations, equation 1, 2, and 3, and 4 now, are only true when the acceleration is a constant. So that's these equations. V equals V0 plus AT. Notice if I put a bar on top of the A, then it's true all the time because it's just the definition of average velocity. But without that bar over the A, this is only true when the acceleration is equal to a constant. So there's one of them. Another equation we got was x is equal to 1 half a t squared plus V0 t plus x0. Another equation we got was v squared is equal to v0 squared plus 2a x minus x0. And another equation we got was v bar is equal to, and you can write this just about any way you want. You can just write it as v 0 plus v1 over 2. These equations are all only valid when the acceleration is a constant. Okay, and they're called our kinematic equations. I'm going to label them 1, 2, 3, and 4, and I'll probably be, if I can remember, I'll probably be referring to them as 1, 2, 3, and 4. Anybody have any questions with that? Okay. Uh, I'm going to go ahead and call it. Uh, I wasted the beginning of class. I feel bad about that. I've got enough time. I could do one more thing. Well, let me go ahead and do that. No, that one's going to take too long. All right. Let's try another one. I'm going to do a different example. Let's say A of t is equal to 3t plus 4. Okay. Clearly, 3 has to have units of meters per second cubed, and 4 has to have units of meters per second squared. And what I want to do is assume v of 0 is equal to 1.00 meters per second, and x of 0 is equal to 2.00 meters. Find v of t and a, or excuse me, and x of t. So this is basically the same process I just went through in deriving equations one and two, but now I'm doing it when the acceleration is not a constant. So this is another type of problem you're going to need to be able to solve. So solution. I'm not going to use indefinite integrals this time. I'm actually going to use the values. So I have 3t plus 4. I'm going to multiply both sides by dt. That's equal to dv over dt. The 3t plus 4 being the acceleration has to be equal to dv over dt. I can now multiply by dt by both sides, and now I can integrate both sides. This side I'm integrating from t equals 0 to t, and this side I'm integrating from v equals 1.00 meters per second to v of t. Okay. So when I do get this integral, I end up getting 3 halves t squared plus 4t uh, evaluated from 0 to t is equal to, in this case, it just becomes v of t minus 1.00 meters per second. I'm going to drop that unit in a second, just keep track of them in my head. So now from this, I can say that V of t, notice the t equals 0 is going to give you nothing but 0 on the left. So all I have left is the 3 halves t squared plus 4t. And then I pull that over to the other side, the 1 over to the other side. This is going to give me 3 halves t squared plus 4t plus 1.00. That's my v of t. Notice this time I didn't use an indefinite integral. I actually just plugged in the initial velocity of 1.00 meters per second. Now this v of t is actually, again, equal to dx dt. So 3 halves t squared plus 4t plus 1.00 is actually equal to dx dt. So I'm going to again multiply by dt. And of course, I have to do that to both sides. But now I'm going to integrate, and I'm going to integrate from t equals 0 to t on, or excuse me, I put those range of integration on the wrong part because that's actually an integral in position. So this is going to be from x0 equals 2.00 meters to x of t, which is what I'm solving for. And this one's going to be from t equals 0 to t. Now, when I integrate the left-hand side, this becomes basically 1/2 t squared plus 2t squared. Ooh, this is t cubed. Sorry about that. That's going to be cubed. And the fact that it was cubed is what got rid of the 3 in the exponent. I mean, in the numerator. And then the 1.00 is going to become 1t. I don't really need the 1.00, so I'm just going to leave off that and just write it as just plain t. And that's the left-hand side, but I have to evaluate it from 0 to t, which is just going to be the same thing. 1/2 t cubed plus 2t squared plus t. And this side's going to become x of t minus 2.00 meters. So finally, I can say that x of t, which is what we were looking for, is equal to 1/2 t cubed plus 2t squared plus t plus 2.00, and that is the x as a function of time. So that's another type of problem you should be able to do. I finished this 1 minute early. I think the free fall problems that are in towards the end of this section, which we'll cover next time, I think they're pretty easy for you guys to get started on it, but I'm definitely going to cover it next time. We'll start off with example 2.9. Make sure you chat at me your first and last name if you haven't already done that. You folks are free to go, and I'll wait for the last person to leave in case anybody has any questions. Thank you, and I will see you later.
I have a quick question.
Yes,
With
ma'am.
the portion that we're looking at right now,
Hmm.
uh, a lot of this is really hazy for me. I remember learning it, but it's been a while.
Hmm.
So what specifically could I review to get stronger at this, like kind of remedial-ish? Because the physics primer helped a lot with a lot of kind of refreshing.
Right.
This wasn't in there.
Uh, there is a section called Variable Acceleration Integral Calculus that
Yep.
starts on page 44 of your textbook. So you want to read that. That's basically the same thing I did here, except they do it with symbols.
Okay.
So I would watch this video again. I would read that section on variable acceleration, and then I would go to the actual problems in the back. And let me point out a specific problem or two to see if they have any in here. Because what you need is a couple of examples where you can do just what I did. Literally, just have my notes right next to you, and you write down and follow step by step what I did. Uh, if you look in, it's not 2.7, it should be variable acceleration, section 2-8. So, uh, problem 72 and 73 at the end of the chapter. Those are ones you could do for extra help or extra experience. I
Okay.
don't really see any more. In fact, two is supposed to be an easy one, but it doesn't have the answer in the book. But if you work it and show me what you did, I can tell you whether the answer is right or wrong.
Okay.
Same thing with three. Three is a level three problem, so that's supposed to be a little harder. I don't necessarily want you trying that to learn anything, but I'm also looking now in the general problems to see if there's any similar problems that might be easier for you to use. I don't see one jumping out at me yet. Let me see.
For
That's
the
not it.
problem, so I wrote down 72 and 73. Are they on page 72 and 73?
No, they're at the end of chapter. There's a chapter section at
Oh,
the end of
in
chapter
the
two.
questions.
Yeah, they
Okay.
start around page
Okay.
48.
Gotcha. Okay. I'm gonna write that down.
No problem. Double checking right now still to see. I don't see any accelerations as functions. Nope. Nope. They didn't give you any more than that. But if you need more, I can make up more. And you'll run into a couple on the practice test as well. So
Yeah.
that might help you.
Okay. All right. Thank you.
All right. Have a good one, Jonna.
You too. Thanks.
Julianne, Wyatt, anybody else have any questions?
I have a question about the labs.
Yes.
So are we able to do the labs at home or are we supposed to go into the campus to do them?
No, you're doing them at home. You're welcome to come up and get help on campus, but the labs are written in such a way that we have an addendum where you can take. In some cases, I'll give you the data. In other cases, you'll have simulation software that does it, stuff like that. But there's an addendum that allows you to do the same labs the students do, only doing it at home without all the equipment and stuff.
Wait, so how do we do the this lab with like the rail car thing or whatever it was?
Rail car. Okay. Are you talking about motion detector lab or the analyzing motion lab?
Let me check real quick.
Okay. Now you do know
But it
that
was
this your class meets like, or I actually hold a session at 10 a.m. on Thursdays. Are you aware of that?
yeah.
For your lab? Okay, just wanted to make sure that that wasn't what was missing. So that's where I come on and tell you exactly what you have to do. If you can show up at that time, that's great. If you can't, it's not a big deal. I still post it to my YouTube channel, and then you watch it, and you'll see exactly how to implement it. But that's what you're supposed to do, anyways.
Yeah, it's the motion detector lab.
Yeah, so what I'm going to do probably, because I did this with my other class, I might do the motion detector lab this week. I might do the analyzing motion lab this week. I haven't decided yet, but I'm probably just stick to the motion detector lab. So let me do this for you, and this will probably answer all your questions the most easy way possible. In your class, I'm going to put up modules. I'm looking at the modules right now, and I will post week 3 But with week three, I'm going to have a lab module like I told you guys about last week. And in there, I'm going to have not only the lab for motion detector, I'm going to have actually, I still already do for two. That was motion detector. And you said it was motion detector that you were asked about, that you were asking about, Wyatt?
Yeah.
Okay. So I'm looking at, let me go ahead and share my screen. I'm looking at right here's week two. So this is your Word document that you would normally do in the face-to-face lab. This is the document that explains how you're going to do it today or on your own at home. And these are comments that I've made in past lab reports that have been turned in. So you should look those over to make sure you don't miss any careless mistakes you've made before you turn it in, and then you turn it in here. So down here is all the graphs and videos and stuff like that that you can use. So all of this stuff is used to help you fill out the the motion detector lab itself. Does that make sense, Wyatt?
Yeah.
So that's it, and that's all I explained on the video as well. So if you just look at that, it'll say, you're gonna, get this graph from, the link down below. You click on that, you can see the graph, and then you just fill it in.
All right.
Okay. Let me know if you need any help. We can set up a private Zoom meeting, just you and I to go over it. Or if you want to meet on campus, I can help you walk through it that way. Whatever you want. Just let me know if you need any help. You have until Thursday at 11:59 p.m. to get it turned in.
All right.
All
Oh,
right.
by the way,
Yes.
I don't know if it was accidental, but I think you posted like the last few labs accidentally, like the nonlinear graphing 2, springs, Newton's second law, and ballistic pendulum.
Those all came up on the course.
Yeah.
Okay. Yeah, that's the problem when you copy all your big stuff from a previous class. Sometimes the things come in and they land places that I don't know about. So just ignore everything except the modules. So when you come into my class, come in and go to modules and look at that and ignore everything that's out of the module. So if it's not in one of these modules, like practice test module, chapter practice module, online test module. If they're not in these modules, then you don't have to worry about them. But thank you for letting me know. I'll try to figure out where all that stuff is and make sure y'all don't see it anymore. Okay.
All right.
All right. Thanks again, Wyatt. Have a good one.
Thank you too.
All right. Well, I guess that's it. Have a good one, everybody. Bye bye.